afternoon, class. Our topic today are orifices at the bottom of tanks, otherwise known as just drains. The drain is part of everyday life. You see them all the time. However, we don't really think about all the science that goes behind how a drain works. Imagine a sink. When water falls in the sink, it'll drain through to this drain right here. However, no one really thinks about all the science that goes behind it, how they pick the optimal drain and the flow rate and everything behind it. But as engineers, we're able to calculate how fast it goes and all of the data necessary to find an optimal flow rate.
As my partner John just said, drains are a crucial part of any tank or sink system. Here, we have a schematic drawing of what would be a tank you find in your home. As you can tell, there is a Q, also known as a flow rate, which is transferring water into the tank. You can see the water level here, and then as it drains through this, through the orifice, we can see a Q flowing downwards. That is the water leaving the system. It goes into this Pitot tube, where it then is officially out of the system. Here we can see a static head. A static head is from the point where the water leaves the system to the water level. So this can change depending on how much volume you have in the tank. For a real world example of this, we have a water bottle with a hole in the top. As you can see, when I put it under, a small flow of water comes out of that and into the cup. This is an example of water leaving through an orifice.
And to give a close-up, this is what it looks like.
Alright, so now we're going to focus on how to calculate the flow. As you guys can see here, we have an equation. Q ideal is equal to A naught square root 2 times G HS. Down here, we know that A naught is the area of the hole of the orifice. HS is the head, the static head, and G is gravity constant. Here we have CD, which is equal to the discharge coefficient. So now, basically, in the perfect world, we don't include friction. But that's not necessarily the case. In the real world, there's friction, like in anything. And if CD is lower, the Q actual is going to be lower.
So, to recap on what my colleague just said, the discharge coefficient is an important factor that adjusts our calculation from the ideal world to the real world. In theory, without things like friction or turbulence, we calculate fluid using Q ideal, a perfect flow through an orifice. But in reality, there's always energy losses because of friction, the shape of the hole, and how water interacts with its surrounding. That's why us as in engineering, we use the discharge coefficient in the tools this calculation for accuracy. We also talk about the area of the hole and the water static head, or the height of the water above the hole, impact and how it impacts the flow rate. These factors together determine how much water flows out and how fast. So whether it's a tank in your backyard or a water bottle nozzle or a massive dam, then the discharge coefficient is key to make sure everything works as planned. So thanks for learning about the discharge coefficient with us, and next time you see water flowing out of the hole, you will know there is always some fascinating science at play.
Thank you for watching.
Thank you for watching.
Thank you for watching.
And thank you for watching.